We now dive into some method details that are essential for your understanding of the whole course. We start with a reminder on the two different approaches followed in DEM simulations. First, this is the so-called hard sphere approach, which uses Newton's law of motion in the integral form. Integral means that we consider a pre-collisional superscript 0 and a post-collisional superscript t instant in time. Here vi denotes the translational velocity of the eth particle and omega I the corresponding rotational speed. During the collision, a certain amount of momentum j is exchanged in an infinitely small amount of time. Note, all further explanations of the variable symbols are available in the nomenclature and abbreviations document available in this section. The hard sphere method is illustrated in this animation. The decisive disadvantage of this approach is that enduring contacts cannot be modeled, meaning that multiple collisions on a single particle cannot occur. Therefore, and due to other drawbacks, we will not discuss this approach further. In contrast, and very often, the DEM is synonymous for the soft sphere approach illustrated on this slide. The soft sphere approach solves the Newton's equation of motion in the differential form, which is what you see here on the bottom. On the right-hand side of these equations, we have the sum of the forces as well as that of the torques. Newton's equation of motion translates into a large set of ODEs, i.e. two vectorial quantities per particle, which are then discretized in time. You see an animation of how this method works in principle here on the top left. Details of this time discretization are summarized on this slide. The so-called velocity-Verlet two-step integration algorithm is typically employed, which is an explicit time integration method. It consists of a half velocity step to obtain an intermediate velocity v at t plus delta t half. The position xi is incremented for a full step. Subsequently, the forces are updated at the new positions and velocity coordinates. Finally, the remaining half velocity step is performed. As you can see, there is no big magic when solving Newton's equation of motion. There are two things, however, that I like to note. First, for more details related to time integration methods, please see the separate document Time Integration DEM. Second, note that similar things as for the translational velocity also apply for the rotational direction. The rotational speed replaces the translational speed in this algorithm. However, the rotational position phi is not updated directly, but via so-called quaternions. More on this later. This is it already for the method's basic. We now come to another small recap section, the contact force models. This is a crucial section since it allows us to understand the critical input parameters of a typical DEM simulation. Let us therefore focus on so-called viscoelastic models, which are an important group of contact models. These models model contact forces in the normal direction, here denoted with Fn, as the sum of an elastic and viscous force component. This sum is then bounded to be always repulsive. You can imagine if the viscous force component is large, this contact force would give attractive forces, which is clearly unphysical. We now have a closer look on the simplest viscoelastic force model, which is the linear spring dashpot or hook model. Here the elastic force depends on a stiffness parameter Kn, which is related to the effective Young's modulus of the colliding pair of particles, as well as an effective radius of these two colliding particles. As you can see, there is nothing magic. Larger Young's modulus results into a larger stiffness and hence a steeper increase of the contact force with the normal overlap delta n. As you can see, there is nothing magic. Larger Young's moduli result into a larger stiffness and hence a steeper increase of the contact force with the normal overlap delta n. For the viscous component of the force, a damping coefficient Cn must be specified. This damping strength is directly related to the coefficient of restitution epsilon n, a quantity that can be measured from experiments. Note that there are analytical relations relating these quantities, as developed by these two authors some time ago, which are summarized superficially here on the right. Further details are available in the document Linear Spring Dashpot, also available in this section of the MOOC. What we have discussed so far is the normal contact force. This was indicated by the superscript n. We now shift to the tangential direction. Here the situation is similar, as you can see here when looking at the spring and the dashpot element below. However, things are a bit more complex since we need to allow sliding in the tangential direction. Hence, there is a need for a frictional element in series with the spring dashpot element. Considering that we also want to model sticking, we arrive at the following expression for the magnitude of the tangential force. As you see, this tangential model requires the knowledge of the normal contact force, since this force is relevant for friction. Conceptually, the behavior is sketched below. Essentially, we cap the tangential force by a critical frictional force. A final hint. This model requires the tangential overlap delta t, which is integrated on a per contact basis in a DEM simulator. Hence, it is often called the history force model, since it accounts for the tangential deformation history of each individual contact. We now round up our excursion to the DEM basics with useful expressions for the contact time Tc. This is important since we have seen that the DEM essentially consists of a large set of ODEs that are discretized in time. Hence, there is a need to set the time increment for this discretization, which is denoted as delta t on this slide and should be smaller than the contact time. But how much? As a relatively conservative rule of thumb, the time step should be 10% of the contact time. This contact time is affected by the normal contact force model, and two approaches exist to calculate it. A stiffness-based contact time, see left, and the famous Rayleigh time for a particle, see here on the right. Fortunately, both approaches show the same scaling, which is that the time step, and hence the contact time, should be directly proportional to the particle size and the square root of the density, and inversely proportional to the square root of the Young's modulus. And that's it. Some DEM simulation tools will calculate these contact times for you even on the fly, which means during a simulation, and choose an appropriate time step. For you, it is essential to remember the scaling with the particle properties, which might help you to drastically decrease simulation times. For example, it is usual to use much softer particles in a DEM simulation compared to the reality. Adequate interpretation, e.g. by normalization of the results, is often sufficient to draw proper conclusions. Now, enough of theory and models. Let us progress to some results to conclude our session on the very basics of the DEM.